So by taking the total derivative of m with respect to temperature, pressure, and all the molar components that make up the system, we were able to show that the total molar property of a system is just going to be equal, should be a bar here, is just going to be equal to the sum of the moles of a species times its partial molar quantity. Okay? Alright, so that's what we showed with this right bracket. But now let's focus on this left bracket, because the result of this left bracket is actually going to give us a fairly useful sort of equation to understand the thermodynamics of mixtures. Okay? And that equation is going to have a name. Alright, so the left bracket gives this relationship. Okay. Where dm molar, which just as a reminder, well actually I'll get to that part in a bit. Dm is equal to these partial molar derivatives plus the sum of mi bar dxi c. Okay? So this is what that left bracket gives us. But what we should also be reminded about is from our relationship on the previous page, we got that m squiggly of the entire mixture is equal to this. And so this derivative is actually just the derivative of xi mi bar. So what we could do is we could actually apply the product rule to expand out that derivative. And so I'll pull the summation out front, but what we get is this. Okay? Alright, and so when we expand it out, we get these two terms, and we see that on both the left hand and the right hand side we have that same term. So we could get rid of those terms, and then we could rearrange the equation to this form. Minus the summation of xi dmi. Summation is going to be equal to 0. Okay. Alright, and so what this equation is telling us is that any changes in the molar quantity for a particular species i's as a function of pressure and temperature, those changes have to be balanced out by the changes in the partial molar quantities. Okay? And so what I'll write is that this equation must be satisfied for all changes in pressure, temperature, and mi bar. Okay? So that's, I admit that's a somewhat abstract statement. But this may make more sense if we take a look at a specific molar quantity, specifically at the case where m is going to be equal to the Gibbs energy. Okay? And so now we're going to have dg, dp, constant t xi, dp, plus dg, dt, p xi, dt, minus the summation of xi dgi bar, which we know is just written as mu I. Okay? All this is equal to 0. But for these partial derivatives on the over here on the left, we know from our fundamental Gibbs equation that this one is just equal to molar volume. This one's equal to negative entropy. Okay? And so combining all these things together, what we get is that v dp minus s dt minus the summation of xi d mu I is equal to 0. Okay? And so this equation has a name. It's known as the Gibbs-Duhem equation. Right? And why this equation is important enough to have a name, is that it gives us, or provides us, a constraint for how changes in the chemical potential mu I should behave. Right? And so the reason that that's important is because the chemical potential, or the Gibbs energy, is not something that we can measure directly. Right? In order to figure out its value, we always have to come up with some sort of mathematical model. Right? Now, to determine whether our mathematical model actually makes sense, what we would have to do is we would have to plug in our mathematical model into this equation and then see if at the end we get a value that is equal to 0. Okay? If that happens, that's good. That means our mathematical model, at least, is thermodynamically consistent. If not, that tells us our mathematical model for mu I is nonsense and should not be used. Okay? To make this a little bit easier to follow, so let's examine a two-component mixture at constant T and P. If it's at constant T and P, these two things go away. Okay? And then we could then rearrange the equation to this form. x1 d mu 1 plus x2 d mu 2 is equal to 0. Alright? So, mole fractions, those are just things that you would know. But when it comes to the chemical potential, basically what this equation is telling us is that only one of the chemical potentials needs to be determined. Okay? And if you determine one of those chemical potentials and look at the changes of that chemical potential, so let's say you determine d mu 1, then you could just rearrange the equation and then determine d mu 2 very easily.